All right, 710. I might call it 710 Part 2 or Electron Configuration Part 3. I don't know. We'll see. But it's going to be more electron configuration stuff. We already did 710 short form in the last one. Then for the worksheet, okay, probably you're going to do Part 2 and Part 3 on this worksheet for this lesson. And then we'll eventually get the whole thing done, okay? But I think I'm going to probably have another video on that right side. Okay, so I think I can get all that done right here. It's one thing about electron configuration and this whole chapter, you'll see, it's a lot of information, a lot of like things you got to memorize. But once you get it down, it's pretty easy. Once you know the pattern of electron configuration, it's not so bad. So, you know, I won't go through it over and over again. You've seen this, and you can go back to the other videos if you want to see them. But like I said, always know the order that atoms fill up in, you know, 1s and 2s, 2p, 3s, and so forth. I could probably still leave it up there. Now I'll try to work on the middle of the worksheet. But I don't really need... Well, actually, I am probably going to use this little... I think it's starting to look pretty bad, isn't it? Well, I don't know. Let me just erase it. I don't know if I'm going to use this or not. I might end up saying, I'll just erase it. But you should know the order of the hotel rooms, how they're all organized. So, you know, I could even, how much, yeah, I have a little space here. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, then 4f, then 5s, p, df. I went kind of messy there, but it'll give me more space here. We'll take our helicopter away from Hog Hotel. All right, this will give me a lot more space. All right, so then, you know, remember again, it tells you on the first floor of the hotel, you only have 1s. Actually, that's going to come into today's lesson. I'll just go right to it. Okay, so now another thing about interesting or kind of, I don't know, it might seem just random in the notes. Like, look at all this. I just tell you all this stuff more about electron configuration. You know, these terms like here, Aufbau, Hund's rule. This is back on 7.9 actually. We can go back to 7.9. But there's all these terms, all these vocabulary words, and then you have all these vocabulary words here. It's all like, what is all that? So yeah, it's just factual information. It makes it a little bit easier maybe than some chapters, some things we've done in chemistry. So all right. In fact, I'm going to go back and go through all those as we do this. So the first thing, on Part 2 of the worksheet, let's kind of look at this, and I'll tell you how to do it, and I'm going to refer back to some vocabulary you see here. But on Part 2, it says, referring to your energy level diagrams, write the symbol for each atom or ion, then write the regrouped electron configuration. Okay. I don't have my worksheet, so I'm going to have to open up my computer. I put it asleep. Please wake up, computer. Let's just sit here. Oh, it woke up. Great. Okay. Sometimes it doesn't because my poor computer is old and it had to have some work done on it over the holiday time. And okay, so here we are. Oh, boy. Let me just do this because I don't have a worksheet in front of me. Okay. I want to do the one that's Scandium, which is letter C. Okay. Okay, that's all I need to know. Computer, you may go back to your dream or whatever you're doing there. Okay. In fact, I want it off. Okay. So, letter C is Scandium. Oh, and I even wrote SC up there already. Okay. C is Scandium. Okay. It says, referring to your energy level diagram, write the symbol for each atom or ion, then the regrouped configuration. Okay. For Scandium, what's the electron configuration? Now, remember, I know the shortcut now from the chart, and I know that for Scandium, these are all the S blocks. So 1, 2, 3, 1s, 1, 2s1, 3s1, 4s1, 4s2. Then after 4s comes 3d1. 3d1. Now, if you ever forget that, then go over here to the little diagonal, and it will show you 1s, 2s, 2p, 3s, 3p, 4s, then comes 3d. See, 1s, then comes 2s, 2p, 3s, 3p, 4s, 3d. Remember they dropped down one. I told you Hog Hotel had an earthquake. All of the D's dropped down one level, and all the F's dropped down 2 levels. Okay. Okay, so back to this. So Scandium goes all the way to 3d1. That means everything up to 3d1 is full. Okay, so hopefully you remember. So we go through all of them. First, you go through the 1s rooms. They fill up. Then you go to the 2s. Let's do it this way. The 1s, then you have the 2s, then you have the 2p's, then you have the 3s, then you have the 3p's, then you have the 4s, then you have the 3d1. So it goes all the way to 3d1, but now what are these numbers? You should have this memorized. If you know if an s is full, it has 2. And I think I got it right there. S, it has 2 electrons. S to S2, it has 2 electrons. If the p system is full, all the p rooms, p, then it's going to be p6, 2, 4, 6. 3s is full, 2, 6, 2. So you should know that. Hopefully you picked that up from the other lessons. But, you know, once you know the top block location, the highest block location for Scandium, everything before it was full. So it's not too bad. It gets a lot easier now, okay? Especially because you can use a chart, or you can use the, or just memorize it. Just know 1s, 2, 2s, you know, you'll get it. And really, you pretty much only have to memorize up to the 3Ds, where you see here from 1s, 2s, up to 3Ds. We don't really go much further than that. But now I say that, but now there'll be questions on it. So you do need to know. So, you know, either for this, probably through this little chart method here is the best way. Okay, here we go. So this is called the ground state electron configuration. Now, this, you might not see this written on the worksheet anywhere. An E configuration is written that way, a little shorthand sometimes. Ground state. And it's like saying every electron will be in the lowest possible level. In fact, let me show you a little vocabulary word that's back on 7.9 called Aufbau. Aufbau process. And what this means is, it's just a German word that means building up, like building a house or something. But every electron, okay, here's the way you say it. If an atom is completely empty, all of its orbitals, the Hog Hotel is completely empty, and all the Hog electrons are all out there. I'll just draw them up, down, wherever they are. They're all out on the beach. They're going to now come in and fill this up. Every electron will always be added in a way so that the atom will have the lowest possible energy, the lowest possible potential energy. Now, let me tell you a way to think about that in terms of like, I don't know. I just have these blocks, I don't have any blocks, but I have these containers. But I'll just show you. This is kind of goofy to even think about it this way, but well, if I'm going to pile these three things up and make a little tower out of it, my little boy likes to make towers out of things. I don't get the chemicals though, but all right. So like I'll put this one down, then that one will go next, and then that one will go next. Okay. So if you're on the ground, it makes sense. So if this were the ground down here, 1, 2, 3. So right now, this is put in a position, it's the lowest possible energy that it can be in, okay? Now, if I put it up here, I'll say, I'm going to put this up here or higher. Well, look what happens. It just falls back down because of gravity. Well, it's the same way with the electrons. I can't just say to the electron, now, this is not 100%, but it's close enough to help you get the idea to be true. If I were to say, I'm going to put an electron up here in 3s, well, I can't do that because the nucleus attracts the electron. But what happens first, you got to fill up the bottom levels, and then you move up. So this level goes up, then that level, then that level. If I don't go in order, if I fill these two up and say, I'm going to put this in 4s, I can do that. Just say if I have 1s2, 2s2, 4s1 or whatever, I could do that, but it would not be the ground state configuration. It would not be stable. It would be what's called an excited state. That's actually the next lesson we'll talk about later. But anyway, what that means is energy is added to the atom. And so the electron jumps. Well, in the very next moment, it's just going to fall back down. So the rule is electrons have to always be added in order from the ground up, the ground state up. Now, that even includes Hund's rule. Excuse me. Hund's rule is the next little vocabulary word, and I've already told you, but it says that when you get within a subshell of P, D, or F, when you go to a P system, 3P, 2P, 3D, or 4F or 5F or 28F or 28P. The electrons will always be added like this. Singly filled, then they'll double fill. Well, actually, that's Hund's rule, but it's also based on the Aufbau process, meaning you would never want to add the electrons in a way that would not be stable. Now, I can't really show you this with these pieces. If I had some Bohr magnets, I could show you that. And I could probably show you, but not exactly. But like, if you put two magnets together, in opposite sides, but my hands, opposite sides they attract. But if you put the same side, they won't attract. They'll repel, okay? If you put the same side, the north, repel, south, repel, but north and south will attract. Okay, well, anyway, because when they're written this way, all electrons are negative. I'm sorry, I said it wrong. All electrons are negative. So if I put two electrons in the same room, look at what's going to happen. Now, I mentioned this in the last lesson. If they have opposite spins, they're able to be in the same room if one's going clockwise and one's going counterclockwise. But that is not perfect. That means their spins have to be exactly the same speed in the same place, pretty much right relative to each other the whole time. If they get off just a little bit or a little bit faster, or this one's a little bit slower, now they're going to repel. Well, so the point is, this is a lot better. It's a lot more stable if they're in two separate rooms than in the same room. And so so electron 1, 2, 3, 4, 5. Number 5 goes here. Electron 6 goes in its own room in the P system. Then the next electron will go in its other own room. That's Hund's rule. They singly fill. Now, at the next point, you might say, well, where will the next electron go? In building up, you might think, well, why don't they go up here? Well, you could, but the problem is this would take more energy. This would be, if you put the electron up there, it still would fall down, okay? The nucleus can pull it, and it would just fall down here, but with an opposite spin. So even though they have to share, this is more stable than having the electron up there. That would be not a ground state or excited state, but it would be more stable. What a mess I'm getting on the board there. Okay, one finger's clean there. You go there, then, so Hund's rule, you single fill, then you double fill. Okay, and then we just continue up. So in other words, all that means is they always fill up in order from the lowest energy. So the atom will have the lowest overall energy as we move on up. And again, what would be lower energy? Having two electrons, one in each room? Would that be more stable for the whole atom? Or would it be better to have them in the same room? And so, no, it's more stable when they're in separate rooms at that point. Or separate rooms at that point. But now that one will be one shared and the other separate. Okay, all right. One more thing about Hund's rule, and it says that if you have the electrons singly filled, they will always have the same spin. That's why you get to draw the arrows up, up, up. So if you have just 3 electrons in the 3p system, one in each room, they will all have the same spin. There's a neat thing about this, and I'll tell you about that in the next lesson as well. All right, now let's go back to this part. So a lot of this I'm showing you is just information, and it can be kind of like boring, like, oh. But hey, it's easy though, isn't it? Compared to a lot of things we've done in here. Okay, so back to this. I was going to do part 2 on the worksheet number 3, and I kind of abandoned, but I'm back to it again. Well, here I'm finally there. Part 2C, I'm sorry. All right, this is not part 2C. Oh, and I wrote that up there, and I said it, but I didn't. Okay, part 2C, what they want you to do is first, you write down the symbol SC for scandium. Not for SC, but for scandium, okay, which is SC. Haha. Okay, all right, so, because it would be USC then. All right, so scandium is SC. Then I'm going to write what's called the regrouped electron configuration. Now, this term, I don't really hear this anywhere else except it was in one of the books. I went through many different textbooks when I prepared a lot of this stuff. I would try to like hopefully try hard to make this ultimate worksheet. That if you could do this, you could do anything from any textbook you get on chemistry. You could do anything on electron configuration, everything they can ask you. Just about. I didn't put everything on here, but just about. Okay, so what do I mean by regrouped electron configuration? Ground state, they're all in the same, they're in order. Regrouped, you're just going to group them according to the floors of Hog Hotel by energy level. So in other words, I'm going to put all of 1s together, all the 2s together, and I'll put all the 3s together. You see there's a 3 over here. So it'll be 1s2, then I'll put 2s2, 2p6, then 3s2, 3p6, 3d1, then 4s2. Okay. Now, the only reason I do this is it's just more of like kind of understanding a little bit about the levels in the Hog Hotel. There's not going to be a whole lot of reason that you really have to know this, but sometimes it's asked, and so I just want to bring it up. So here's the deal. Now, a while back there was a model of the atom called the Bohr Model, and it was by Niels Bohr, and we're going to talk about that. Can you see all those? Oh yeah, I guess you can, sort of. Okay, well here's how it works. Niels Bohr used what's called the Planetary model of the atom. He believed in that, and well, that was his theory based on Rutherford as well. But it turns out now we have the quantum model. So I'll talk more about the quantum model as we move on. But one thing I'll mention here is that it is okay to assume that electrons in an atom, as you move from level 1 to level 2, level 3, level 4, and so forth, level 5, 6, 7, 8, 9, the electrons in those levels are physically farther from the nucleus on the average. On the average, they are. And I'll show you what I mean by that later. I'm going to have to go that in another lesson after this. I have to go over that in another lesson. But even SPDF, so it's like 1. Actually, Hog Hotel kind of shows it to you there. I could just label the floors. But like, if 1, level 2, level 3, level 4, and so forth. So you can think of them as being physically farther from the nucleus. If positive, if that's the nucleus, think about like the planets going around the sun. That's level 1, level 2, level 3, level 4, level 5. Okay, and then 6, 7, 8, 9, 10, and they go infinitely. Okay, now, even the SPDF are that way too. So let's just say you have one S. Well, then let's just say you have S, then you have P. You have 3 of them, whatever. Then you have S, P, then D. Then you have S. So S, SP. So 2P is a little farther electrons. They're farther from the nucleus than the 2S. 3Ds are farther from the nucleus than the 3Ps or the 3S and so forth. But now it gets kind of weird with the 4S, and I'm going to show you that later on. But still, they are. So the levels are, energy levels are 1, 2, 3, 4. In fact, we call the principal quantum number. In fact, I will even write it there. N equals 1 means you're at level 1. N equals 2 is called the principal quantum number at level 2. N equals 3, level 3, and N equals 4, 4. We're gonna get to that in just one moment. I'm jumping ahead of something. Let me kind of back up a second here. All right. So first, just understand level 1 is closer to the nucleus. 2, 3, 4, 5 gets farther and farther away. S in any level is closer to the nucleus. So I guess in the hotel you would think we got the wing S, P, D, F. It's like the S, then the P's get a little bit higher, then the D's get a little bit higher, then the F's get a lot higher. Okay. So whatever. You can think of it that way too. All right. So here we go. So this is the regroup configuration. Now, I don't exactly know why, but many years back, like in the early, 1920s, instead of saying electrons in the 1 level, or in the first level of Hog Hotel, I guess I will fix Hog Hotel over here a little bit. In the first level of Hog Hotel, the 1S, then 2 is the 2S and 2P, then 3 has S, P, and D. I don't want to mess this up and get you confused. 4 has S, P, D, F, and then on and on. Okay, we call number 1 the 1 shell. N equals 1 shell. Everything in 2 will be N equals 2 shell of electrons. N equals 3, N equals 3 shell, N equals 4, N equals 4 shell. Think about this kind of like being a balloon inside a balloon, inside a balloon, inside a balloon, inside a balloon. If you have many balloons, and because the balloon plastic is negative, made of electrons, each level stays away from the other level, okay? Well, that's called the 1 shell, the 2 shell, the 3, the 4, the 5. Or actually, they technically they refer to it as the n equals 1 shell, n equals 2 shell, n equals 3, n equals 4. Well, I don't know why they did this. I don't know if you can even read that too good on there with my handwriting. But they decided that the 1 would be called the K shell, capital K. The 2 would be called the capital L shell. N equals 3 would be called the M shell, capital M, N, O, and P, Q, R, and it keeps on going. So, the K shell, the L shell, K, L, M, N, O. Can you see those letters? I guess you can. K, L, M, N, O are shells number 1, 2, 3, 4, 5. I don't know why, but they did that, and it pops up sometimes. So, okay, here we go. Now, I did part 2. I put scandium in its regrouped form. Some elements are not going to change at all. Like if I did 1s2, 1s2, 2s2, 2p6, 3s2, 3p6. Say if you stop right there, 3p6 would be argon. Well, argon would be, if I had argon, if I did argon, 1s2, 2s2, 2p6, 3s2, 3p6, well then, that's shell 1, shell 2, shell 3. There'd be, when you regroup it, it would be the same as it was ground state or regrouped. So some elements that you do will be the same. Okay, but if they have like a transition metals, which I mean the ones that are here in the middle, then they might change a little bit. They will probably. Okay, here we go. Now, if you wanted to pause it right now, you can do all the rest of those. I did C for you. You could do A, B, and so forth. Now let's go to part 3, and I'm going to do for C. Look at letter C. It's going to be for Scandium. I'm going to go straight down the list and do all of these terms here. All right, and we'll tell you the vocabulary as we do it. So I told you it's kind of a boring thing, but it's, you can take a break if you want to. All right, so on letter C, I'm going to go straight down the list. I'll put a C here. See if I can fit this. Part 3. So part 2 looks like that. Part 3, I'm going to put my letter C right here. And the first thing it says, number of valence electrons. Okay. This is a big one. What do I mean by valence electrons? And then below it, outer level electrons. I wrote that. I wrote principal quantum number for the valence electrons, and electrons are in the blank shell. What if I should tell you the shell first? I guess I will tell you that, and then we'll come back in a minute. Okay. The valence electrons in an atom are always the outermost electrons. Now, why does that matter? In an atom, only the outermost electrons react. So if you have HCl, hydrochloric acid, okay? Well, what you didn't know, we haven't done a lot with dots yet or anything like that. Hydrogen only has 1 electron, oh well. But only the outside electrons of chlorine are going to bond or connect with like this to make a bond in HCl. All the electrons that are on the inside are going to stay as part of chlorine. So you can almost think about it like this and say, whatever your outer level that's full, only those are your valence electrons, the ones that are in the outermost level. Okay, so how do you determine what are in the outermost level? The best way to do it is to write the short form electron configuration. To find valence, write the short form. Well, I'm going to show you a shortcut in a moment. And short form is a shortcut. Write the short form E-config to find valence. So for scandium, I already did that actually last lesson, and I can go up here and just write it there. Can you remember how we did that? You look at scandium, and you say, okay, what noble gas comes before scandium? We go backwards, not calcium, not potassium. It has to be group 18, argon. So scandium, electron configuration, electronically, scandium is the same as argon, but then you add to it 4s1, 4s2, 3d1. So 4s2, 3d1. Argon, 4s2, 3d1. Okay. I don't know if you can see that too good, and my chalk is it's surviving. You know what? I don't think I'm going to need this anymore, so I can just write it there too for now. All right, so argon, write the short form. And listen carefully when I tell you. The valence electrons, when you write the short form, they will always be all the electrons, like you have 2 plus 1 is 3, all the electrons that are left over, that are after the noble gas, except, so 2 plus 1 would be 3 in this case. So you'd say, well, a scandium has 3 valence electrons. But now, hold on, there's an exception. You write the short form. The valence electrons are all the electrons that are left over, except you do not count any electrons that are in D10 or F14. So what that means is, if the D system is full, or if the F system is full, then they do not react, as I showed you over here with, they do not react. They do not form bonds. They are not valence electrons, okay? So, and D10, if your D system is full or if your F is full, then it will not count. So, for scandium, how many valence electrons are there? There will be 3. Number of valence electrons, you can put the number 3 right there, all right? Now, let me show you another example. Like, what if I had an, oh, I didn't want to erase that yet. Oh, no, I certainly didn't. Okay, oh, well. Let's say that I have, okay, let's see, scandium is argon 4s2 3d1. Let me pick an element like gallium. Okay, how about that? Gallium. If I did gallium, galliums would be argon 4s2 3d10, then 4p1. So gallium is, on the chart, argon, then 4s2, then you go through all the D's are full, 3d10, then 3p1. Okay, well, if I look at that, how many valence electrons does gallium have? Well, I have 3d10. So the 3d10, those don't count as valence. So it would be 2 plus 1, it'll be 3 valence electrons. 3. Now, I'm tempted to show you the shortcut, but now I'm not going to show you the shortcut yet. Maybe at the end, or I'll tell you another time for the chart, because I want you to know how to get it from the electrons first. Okay, and if you know that shortcut, then you can use it, of course. Okay, the next question on here, it says the number of valence. So that was number of valence are 3, and that's the same thing as the number of outer energy level electrons. The principal quantum number for the valence electrons. Okay, this term principal quantum number, there are 4 quantum numbers for every electron. Now, I'm going to talk about that. I might make a bonus lesson on it, but you don't have to know that right now. But I'll just say this. It's the floor of the hotel. The principal is the hotel floor location. So it'll be N equals. Now, for the valence electron, the principal quantum number for valence, the valence electrons for scandium are found at the level N equals 4 and N equals 3. So some are on level 3 and some are on level 4 of Hog Hotel. So N equals 3 and N equals 4. Now, you could just write 3 and 4 in that blank if you wanted to. But I think it might be better to write N equals 3 and N equals 4. Now, okay, because that way you're telling me N is the, you know the N. I should have even put the letter N right there, principal quantum number. But that way you know it's N. You'll always remember that's principal. That's the floor of the hotel. So go to floor N. They don't tell you that in a hotel, but go to floor N equals 11. Okay, that just means the 11th floor. Okay, that's all it would mean for Hog Hotel. All right, now the next question on the chart is number of valence electrons. Valence electrons are in the blank shell. Okay. All right, blank shell. The blank shell letter. The shell letter. Now, this is a picky thing. I could probably just leave it off. But shell letter would be, are these letters, K, L, M, N, O. For whatever reason, however they made them, maybe it was German scientists, but K is N equals 1. L, N equals 2. M is n equals 3 and n is 4. So it would be M and n. 3 is M, shell M, and shell capital N. Okay? So small n for quantum number, but capital N for shell n. K, L, M, N, O. 1, 2, 3, 4, 5. Hopefully you can see that okay. But K is 1, L is 2, M is level 3, N is 4, and O is 5. So I wrote the same things right there, but it might be easier to read there. K, L, M, N, O. 1, 2, 3, 4, 5. And then, you know, there'll be a P, 6, and it will continue on over and over. All right, we're almost done. Shell letter. Okay, now it says how many electrons are in each of these individual shells. How many are in the K shell? Is it all going to fit? Oh, it's not going to. Oh, you know what? I'm okay. Everything so far is fit. I'm going to have to erase. Well, I can put it to the side here. How many electrons are in the K shell, the L, the M, and the N shell? Okay, so these last few things are kind of picky for me to be teaching it, but you know what? At least you'll know it, and you'll see. There's some times it might pop up. If this is scandium, these are the K shell electrons, everything with a 1. K is 1, N equals 1. N equals 2 is the L shell. These are all the M shell, and these are all the N shell, and 4. So how many electrons are in the K shell? 2. Or I could use my green if I've been using green so far. How many are in the L shell? 2 plus 6, 8. How many are the M shell? 2 plus 6 plus 1, 9. And how many are the N shell? Just 2. Remember that was Hog Hotel. I can take that part off. All right. So I know this is kind of goofy in a way, almost like busy work stuff. But you do work all those in part 2 and part 3. Oh, I was going to tell you that you could skip some of them. Oh boy, I'm going to see if I can find. I got to wake up my computer again here. You can skip something. I know you're probably staying on there. Okay, what can we skip? What can we skip? You can skip. Oh no. I'm trying to remember which ones they are. Oh, the phosphide or zinc. Oh, okay. Mg plus 2. Well, the shells for K, L, M, N, O. I'm trying to think about that for a minute. I guess. Oh boy, I'm very sorry about this. If you want to hold on one more minute, I'm so sorry to be. I don't actually have it right in front of me, but I can tell you. Okay, here we go. I got the answers right here. Oh, okay. You can skip letter G and H, I think, because they're kind of strange. Or I don't know about E. Yeah, just skip. You can skip G and H for this analyzing stuff. Don't worry about that. This is getting to be crazy. But or do I like H? I don't know. G and H. It looks like I crossed out G and H on my paper. Well, okay. Yeah, just do that. Okay, that's all. I'll see you guys. Sorry for that long delay at the end there. I was looking at my own answer key on my scan to see, because some of them might get a little confusing here and there. But this is not a big deal. But I just want you to know all of this terminology. Oh, was there anything I didn't tell you about? No, I'll get the other parts tomorrow, the other words, or the next lesson. I'll see you.